welcome to this session of the course Elements of Mechanical Vibration. We are going to have a short lab session on one of the simple oscillatory system in the lab. So, although all our mechanical systems do have force excitation, and therefore, the vibrations that we encounter are forced vibrations, but it is always interesting to study the free vibrations of simpler system to start with. And in that light, this setup that we have in the lab is called as a trifilar pendulum. And as the name suggests, it is a body that is going to swing around its mean equilibrium position. So, I would like you to just have a look at how the test setup is all about. Now, what we have is a circular plate which is hung by 3 inextensible strings hung from the top frame here. So, you can see that these 3 strings are tied at the top frame and they are vertically taken down, and at their other ends it is connected to the plate and tied to the plate at 3 equiangular positions. So, they are making 120-degree angle at their connection points to the center of the plate, and through this arrangement the plate can swing about its own axis, and the whole pendulum then oscillates about its equilibrium position once it is disturbed from its equilibrium position. Now, you may notice that if you consider this as its steady mean equilibrium position, and I give a gentle angular twist or angular motion to the disc and tilt it a bit in the horizontal plane and then release it from that position, it keeps on swinging back and forth. Now, we all know that a typical vibratory system is when it is vibrating at its one of the natural modes, there is going to be a continuous interchange between the kinetic energy and strain energy or potential energy. In this case, because there is nothing in this particular system that stores the strain energy, we must be having an interchange between the kinetic energy stored in the plate because of its angular motion. That kinetic energy is converted into potential energy. Now, where is the potential energy in the plate? Because when it was at its mean equilibrium position, this is the height at which the plate is located. The moment I give an angular deflection or an angular swing to the plate, what you notice that the string gets shifted from its vertical position to a slightly inclined position, but at that angular position of the displaced point, the string is now going to be the point here and this point is going to have a larger distance between them, and because it is constrained by the inextensible string, the moment I twist this, the increased length is actually cannot be possible because the string cannot extend, and therefore, the string actually pulls the plate up, and that is how all the 3 strings are going to pull the plate vertically up. And so, as the swing happens, the angular motion happens, the plate is lifted up vertically, right, and that is how the 0 potential energy is going to change to a higher level of potential energy, okay, as the height is raised. So, the plate stores the potential energy as it swings on either side, and when I release it, that potential energy gets converted into kinetic energy, and therefore, as the plate comes back to the mean equilibrium position, the entire potential energy goes to 0, but it has gained in expense the kinetic energy, and that kinetic energy then keeps the plate moving in the other side. Now, nothing changes on the other side except the position is on the other side of the mean equilibrium position, but here as well you can see that the distance between these two ends has to be what it was earlier, and therefore, the net effect of that is that the string is pulled up and the plate is pulled up with the string, and that is how on the other side again the plate moves up by some height, gains the potential energy, kinetic energy goes to 0 at its extreme position, and this kind of interchange between the potential energy and kinetic energy keeps on happening, and that is how the plates swings back and forth. And the oscillation that you see here is now a result of the initial disturbance that I have given to the plate. How do I find the natural frequency of this system? Of course, the plate, if it is considered as a rigid mass, now the plate is considered to be a rigid mass and it has its own mass moment of inertia about an axis passing through the center. I would like to find out the relationship between the period of oscillation and the mass moment of inertia of the plate and the mass of the plate. So, basically the period of oscillation of this plate is as a function of the mass moment of inertia of the plate and the dimensions such as the length of the string, the position of the string with respect to the axis of the plate, that is the center of the plate, this radial distance, the length. Using those parameters you can find out the period of oscillation and therefore, the natural frequency of this system. Now, what is the purpose of this experiment? This particular trifilar pendulum is used to find natural so, the trifilar pendulum is used to find the mass moment of inertia of any body whose shape and dimensions are not standard in that sense, so that the mass moment of inertia can be experimentally determined. Now, in that light I would like to show you this mechanical system, an element which is a connecting rod used in the IC engines, and if I want to know the mass moment of inertia of this connecting rod about either its small end or a big end or about its CG, what I can do is I can align the point about which the mass moment of inertia is to be obtained with the center of this disc and place it on the disc, find out the period of oscillation of this entire trifilar pendulum. Now, I will get one reading by placing this onto the plate and another reading I can get without the body in place. So, what I will have from the first data or first measurement is the mass moment of inertia of only the plate, whereas by putting the unknown body or the body whose mass moment of inertia is to be obtained, I will get another period of oscillation of this trifilar pendulum, and that will give me the total mass moment of inertia of this body plus the plate. So, by subtracting the mass moment of inertia obtained from the second reading from the first reading, I will basically get the mass moment of inertia of the object whose of the object that I want to find. Okay. So, I shall just place this connecting rod with its axis aligned to that of the plate, and we shall try and record the oscillatory motion and therefore, the period of oscillation. Okay. So, I look at this, that as we all know that for the derivation of the governing equation and the expression for natural frequency, the underlying assumption is small amplitude of oscillation, and therefore, it is imperative that practically as well we give a very small angular displacement, so that the oscillations are with small amplitude. And you can notice that the plate is generating an oscillatory motion, and this free vibration response can be recorded and we can find out the period of oscillation. Place the connecting rod with the axis of the plate aligned with that of the big end of the connecting rod, so that whatever value of mass moment of inertia I will get will be about the axis of the big end of the connecting rod. And so, to get that period of oscillation, now I will give a gentle initial perturbation or small initial amplitude, and through that, as you can notice that the plate is swinging back and forth, and now we can record the number of oscillations and the period taken for those oscillations. So, one of the simpler way is to simply record the period it takes to complete a certain number of oscillations, and we can now start the data. So, the period for 10 oscillations is 11.9 seconds. Larger number of oscillations will help us in reducing the error in the measurement, but that is how we record it with the connecting rod in place, and one set of measurement can be done without the connecting rod. So, I can keep on taking another set of measurement for only plate in place. So, without connecting rod and with connecting rod, that gives me two values of mass moments of inertia, and by subtracting the two I will get the mass moment of inertia of the object that I placed. So, that is how we find the mass moment of inertia of any body about a particular axis, which is not a standard form and shape, as you can notice here. For standard objects, I mean the objects of standard shape and sizes, we can find out the mass moment of inertia using simpler expressions known already, but for complex shapes it is experimental measurement is quite handy, and that is how this trifilar pendulum can be effectively used to find the mass moment of inertia. Okay. So, let me again give you a glimpse of the whole setup. You basically have these three strings which are vertically aligned and connecting to the plate at the three extreme ends here. So, their radial positions are something that you can measure easily, and the strings are inextensible, so that when the plate swings, it does not allow the plate to I mean the point of connection is lifted up as the plate swings, and this is how the swinging motion happens, and that is our typical vibratory motion. So, the plate looks like this. You can see how the threads or the strings are fixed at its periphery at equiangular positions. So, this system has three strings which are fixed at three equiangular positions on this frame, and these inextensible strings basically connects the plate to the top frame, and these strings are exactly vertical at the equilibrium position of the plate, and it is only when the plate tries to swing about its vertical axis that the point of connection of this string with the plate that changes its orientation. Okay. So, about the vertical axis, this is how it changes. So, the strings are the most important thing in this case is that the string does not extend and the plate swings about the vertical axis. Okay. So, based on this measured data, you can find out the value of this mass moment of inertia based on the measured values. You can also find out the expression for the period of oscillation for this trifilar pendulum, and for this you will realize that it turns out to be a function of the radial position of the connection of the string with the plate, the length of the string, the mass of the plate, and the mass moment of inertia of the plate, okay, or the mass moment of inertia of the plate plus the object which you are trying to measure. So, all these things are going to be a sort of a homework for you to derive that expression. We shall provide you with the values of the various parameters that we have used in this experiment, the dimensional details of it, and also we will provide you the measured data, although from the video record you can always find out the period of oscillation, but we shall provide the required data, the measured data, so as to enable you to calculate the mass moment of inertia.